The Chesapeake heating solution is based on a trio of technologies on a seasonal time frame mode, a hybrid photovoltaic solar thermal panel, a thermal storage system, and a heat pump. The red and yellow lines, which you see in the screen, are the energy transfer between this hybrid photovoltaic solar thermal panel, the water tank, the heat pump, the electric grid, and the building. The hybrid photovoltaic solar thermal panels generate heat to be stored and used for domestic hot water and or indoor heating, and in addition, solar thermal panel generate electricity storage system that can be used by the building system and appliances. Red and yellow lines, which you see. A conventional photovoltaic panel only uses hybrid photovoltaic solar thermal panel. The water tank hybrid panel also generates heat for indoor heating and water supply. The hybrid output temperature is between 45 and 50 generate heat to be stored and used for the suitable temperature for the Chesapeake heating, and in addition, solar thermal panel generating around 20% that can be used by the buildings. The panel works at red and yellow lines, which you see. Conventional photovoltaic panel uses solar or liquid material, stores the thermal energy, also generates heat to support the energy demand of the building in the winter period. In that case, the heat pump transfers the seasonal storage temperature to the building heat demand temperature, which only requires a very low electricity consumption. The Chesapeake pilots apply seasonal storage solutions with bank and a water tank, and with two different positions, under and inside the building. Due to its characteristic one-time charge and discharge per year, which is characteristic for seasonal storage, the heat losses of seasonal storages have an impact. In both Chesapeake pilots, these heat losses can be used as indoor heating for the building space above the storage or for the building space around the storage. The heat pump provides domestic hot water and or indoor heating as well, transferred from the hot water tank to the building and at high efficiencies. In case of an electric surplus, this can be stored in batteries and transferred to the grid. All Chesapeake pilot projects have roof integrated solar panels, hybrid or photovoltaic, and have heat pumps. In two Chesapeake pilot buildings, they offer a seasonal heat storage solution under or inside the building. Our partners. The Chesapeake Consortium has 10 partners based in 6 countries. Ulster University, which is committed to economic, social and cultural developments, is responsible for the design and testing of advanced heat pumps. Electric Corby, a community interest company establishing Corby as demonstrator for future sustainable living, working and transportation, is responsible for the pilot project in Corby. Wanstronk Architectuur, an architecture studio establishing a low-exergy and zero-emission building concept emporium, is responsible for the seasonal storage and tank construction. Eurogrant, a spin-off from the European Project Center of the Technical University of Dresden, is responsible for the administrative and financial management. Edenway, a Paris and Barcelona-based consulting firm specialized in the integral management of innovative and sustainable projects, is responsible for the communication and dissemination. BCN Ecologia, the urban ecology agency of Barcelona, rethinking the metropolis from a sustainable point of view, is responsible for the project coordination. Lavola, a consulting firm dedicated to economic, social and environmental sustainability, is responsible for the pilot project in Manlleu. Ayuntament de Sant Cugat, which is the city council of Sant Cugat del Vallès, with a clear sustainable growth strategy, is responsible for the pilot project in Sant Cugat. Battea, a company specialized in energy efficiency to improve all kinds of facilities, is responsible for the monitoring and management system. And Veolia, an energy and environmental service company and district heating operator, is responsible for the technical and business development. So my last slide, the Chesapeake system. The system is tested in different geographical situations, Mediterranean climate and an oceanic climate. and in different types of buildings. So you see a residential project, an office building, and a sports center with a swimming pool. So the pilot in Corby, which is left above, in the United Kingdom's Northamptonshire, is a residential project with 26 new built eco-homes as part of the Priors Hall development, Priors Hall Park development. Then Manlleu, which is right, is the pilot in Manlleu in Spain, is an existing office building, Lavola's Eco Edifici or Eco Building, showing a small-scale project with limited space for the heat storage, which will be explained in the presentations after these. The pilot in Sant Cugat in Spain, next to the Sant Cugat City Council, is the Eurofitness building, an existing sports center with more than 6,000 users, and including a swimming pool. All pilot projects are simulated and monitored. The behavior of the three topologies of the pilot projects are simulated with Transys 18 and Excel-based spreadsheets. So afterwards, they are compared with the data collected during the monitoring period. Business models and exploitation plans are developed as well. Energy service company business models are applied for the three pilot projects, including total cost of operation, energy savings, both electricity and thermal, a business plan simulation, and improvement proposals. All partners developed an individual exploitation plan, and at an exploitation strategy seminar, all partners selected two key exploitation results. The first key exploitation result is the ChESATOP system to implement a technical solution, a reliable and efficient seasonal energy storage system able to supply heating and domestic hot water in buildings, mainly from renewable energy sources, increasing the self-sufficiency of the building and reducing its emissions. The second key exploitation result is the so-called ChESATOP services, offering a global integrated solution based on energy services where the ESCO takes responsibility to supply the service engaged, such as energy management, maintenance, fully warranty service, improvement of works and installations renewal, in order to guarantee savings and its subsequent economic savings on the deployment of the ChESATOP solution. Thank you.
Thank you very much, René. It was a very good introduction. I think that in that case, some of the questions that you might have right now, it will to be answered during the presentation of the pilot. We are going to give more details. So I ask Neil now from Ulster University to start with this intervention. Good morning, Neil, you are here?
Yes, I'm here. Thank you. I'm just going to share my screen with everyone. If that works with everybody. Can everybody see that okay? Or let's hit that button.
Perfect, we see it.
Thank you very much and good morning, everyone. My name is Neil Hewitt. I am part of Ulster University. We are a regional university in the UK based in Belfast and other campuses around Northern Ireland. So looking at how we have came to be involved in this project and how the heat pumps have evolved during a period of time. Going back to the late or mid-90s, we were responsible for the development of the very first sort of R410A heat pumps used in Europe. And you can see they were ground source units here on a demonstration site in Austria. And when I was younger and fitter, I helped actually install some of these things many, many years ago as part of the process. But new build is fine, and we'll hear from Nick in Corby of the experiences with new build. But our emphasis moved to retrofit, and we developed air source heat pumps. And indeed, this one was deployed in my own house here in just outside Belfast in Northern Ireland to effectively just drop in replacement to replace the oil-fired boiler. You can see an oil tank with a direct heat with a heat pump that heated the hot water sufficiently to maintain the existing radiators and maintain thermal comfort within the home. As we moved forward, we were able to consider some of the harder to heat properties in the UK, and there's approximately 8 million of this terrace type house within the UK that people live in, particularly in urban centres. And so we considered how to retrofit heat pumps and thermal storage with or to these houses. And as part of this project, we also added or used our facilities to look at PV and solar thermal added to these as well. And we delivered a number of publications on that. So we were able to model and deliver our energy storage, which in this case was 600 litres of water, and is now, through future projects, now phase change material. And we're starting to model and deliver these aspects as well. So our publications that arose out of the project, there are a number of publications. These are the 2 journal publications so far. There's a number of other conference publications aspects, but these focus on the use of Transys. Transys is a proven model for building integrated solar heat pumps, etc. And what we used was we used our data from our test houses to verify the performance of these things and then apply these to wider building stocks across, in this case, the UK. Our future work is looking to broadening that across a wider housing stock. But one of the challenges in the project was how to advance the heat pumps. So what CHESS set up exposed us to was a significant challenge of climate management. Some of our test sites have broad or wide ranges in temperature experienced from cold winters to hot summers. So what we were looking at is how to develop a heat pump that would utilize the widest possible capacity it could deliver. And this was done in conjunction with a partnership we have with Emerson, a major manufacturing company of compressors. And we were able to build and test in our test chamber, which is EN 14511 compliant, how this heat pump would perform across a range of climatic conditions. And you see some images of the heat pump in the test chamber and the supporting equipment on the outside. The second challenge was, well, how do you deliver instantaneous hot water? One of the challenges that was thrown up in the early days of CHESS setup was how much space do we actually have for thermal storage? So one of the ways we started to look at that was, well, what can the heat pump do to minimize the space required? So the extreme answer is, how long does it take an air source heat pump to deliver hot water for a shower, for washing your hands, etc., etc. And then putting some common sense on that would say how much storage you'd need. So one of the challenges that came out very quickly when we started working with the variable speed drive compressors and how much they can actually deliver across their speed range is technically, you can't have them running too quickly or they damage. And if you go too slowly, they don't lubricate properly. So, but an unknown challenge, which came quite a surprise to the manufacturers as well, was these control instabilities that we came across. So you would try and ramp up a compressor and come up to, say, deliver hot water as quickly as possible, and then the compressor would become unstable. So there was these speed changes you can see in some of the graphs. This transmitted itself to when you actually saw what the compressor was doing on its operating point. It was running through ranges of speeds across its operation as it tried to ramp up to deliver a hot water demand fairly quickly or a space heating demand very quickly. So this was referred back to the suppliers, and there's ongoing work on how we make these things more stable. And part of that has seen a greater stability in ramping up and delivering compressor power on a more stable platform, if you like, and therefore delivering heat pump output heat. And as a consequence, the system is much more stable, but still takes maybe 4 to 5 minutes. So the minimum storage for domestic hot water is that sort of value, depending on what's needed, as an additionality to the seasonal thermal storage that we already have. So it's been good to understand how the compressors can operate. And just to conclude then, ladies and gentlemen, we have simulated the heat pump and thermal storage operating in typical UK homes. We've extended that work to different UK climate contexts and housing types, and are going to extend that further into European climate zones. We've been looking at how we bring up the new compressor types into new advanced heat pumps so that one unit can maybe cover a much wide range of climate demands. So saving on capital costs and thinking about near instantaneous hot water as an aside. We're solving that problem with control instability issues that we've had to overcome. And it has resulted then, this last work would have resulted in a presentation at the 2020 compressor conference at Purdue in the United States. But unfortunately, due to the current situation, that's been put back till next year. So with that, I will come to a close and say thank you very much, ladies and gentlemen. And hope you're all well and hope to see you all soon. Thank you.
Thank you very much, Neil. That's very interesting. I don't know if anyone has any questions. I don't have any in the chat right now. Maybe we are waiting for the end, wherever you want, but I repeat that if you have any question after every intervention, you can do so. We have time for 1 or 2. Right now, we don't have anyone, so we are going to give the word to Cristina Valles from La Bola, and she's going to explain us the pilot experience in Manlleu. Hello, Cristina.
Hello, everybody. I'm Cristina from Antisys La Bola, and I'm going to explain our pilot experience in our company. Okay, so La Bola has implemented one of the 3 pilot cases of the project in its headquarters in Manlleu, in the Eco Building. The Eco Building is an office building that was constructed in 2006 according to sustainability criteria. It represents the values of the company. It can be visited, so it has an educative and communicative functions. It shows the economic and technical feasibility and utility of applying sustainable criteria from the design and through all the stages of the construction process. And it must be underlined that in 2010, the building achieved the LEED certification for existing building, which it was renovated in 2015. And according to sustainability policy of the company, La Bola is working on the transformation of the building into a nearly zero energy building. So the value of SHES setup project in the company is to approach the building into this goal, which will make a significant contribution towards the aim to be efficient and autonomous in energy. So here we are the data of the building energy demand. So the ratio of energy consumption before SHES setup implementation was nearly 93 kilowatt per square meter. And we can see that the heating and the cooling system represents more than 50% of the energy consumption of the building, which means that it had a high potential of energy savings. Regarding the pilot, it originally consists of a small scale prototype for an office building. However, the initial system configuration had to be modified to adapt to the circumstances of the existing buildings. And in order to accomplish the goals of the CHES setup, and after studying the challenges and constraints, a variation has been built, and it represents a showcase for existing buildings with lack of a space for thermal storage and with renewable potential. So this is the first option considered. It consists of a reduced size tank for thermal energy storage that was daily, not seasonal, given the space limitation of the building. And also it has hybrid panels and a water source pump. This configuration allowed covering almost the heating demand, but only for the third floor of the building. And the rest of the building spaces had to continue using the existing HVAC system that was a boiler and of gas, natural gas and a chiller. One of the most important weaknesses of this system configuration was that the solar thermal energy produced by the hybrid panels could be only used for the winter time, and the energy produced in summer had to be dissipated due to the lack of thermal energy demand in summer in the building. Thus, it was an important amount of wasted energy. So with the aim to optimize this first option, we came up with the second alternative that consisted of an installation of photovoltaic panels instead of hybrid panels and an air source heat pump. So the thermal storage tank and the water heat pump were kept as the previous configuration. The electricity produced by the photovoltaic panels would be used to feed the air source heat pump. The surplus of the photovoltaic panels will feed any other electric demand of the building, the lighting, the computers. And this air source heat pump will heat the storage tank to produce the energy needed. So the solution would provide more benefits in terms of energy savings, as well as avoiding wasting the energy produced in summer. But the system also fits the third floor already. So feeding the entire building would represent a very small contribution to the overall demand and was considered not appropriate. So the final solution is that one, and keeps the photovoltaic panels as the energy production side of the system that feed an air source heat pump that heat this pump the thermal storage, which in this case is the thermal mass of the building slab. So it's where the heating floor is already installed. With this solution, no thermal energy is wasted. It supplies the entire building, and energy savings are greater than the estimated previously. Okay, so here we have the main elements of the installation. It is a 9.9 kilowatt peak photovoltaic installation that occupies 68 square meters. We have an air source heat pump of 60 kilowatt, a buffer tank of 300 liters, and a thermal storage of 33 cubic meters. And now I will show you some images of the implementation process. So construction works started in June 2018 and finished in August 2019. First of all, we relocate the existing photovoltaic panels and solar panels to avoid the shadows and have a space for the new elements. And here you have the images of the panels and the trackers replacement. And then we have these pictures of the conditioning of the roof and the assemblage of the metallic structure that holds the new photovoltaic array. And here we have the structure and the panels already on this structure. Here we have the building of the concrete slab for the heat pump and the buffer tank. That's also on the roof of the building. And here we have the images of the reception of the efficient heat pump. And then here, the heat pump already installed with the buffer tank, and also the connections of the pipes to the existing circuits, as well as the different control elements like sensors and meters. So this one are some screenshots of the control system software. This is the land page of the control system. And for example, this is one of the schematic diagrams to control the setup system. Okay, and this is the results. This graph shows the energy consumption and the carbon emissions of the baseline and the setup system. The setup provides an annual gas consumption savings of 79,000 kilowatt. But on the other hand, despite the contribution of the renewable energy of the solar PV panels, the electricity represents an increase of around 40,000 kilowatt per year. So we avoid the consumption of the existing chiller, but we have the new heat pump. And summarizing, and to finish the presentation, the total energy savings is 64,000 kilowatt year. That is a 47% savings comparing to the baseline. And savings in greenhouse gas emissions are close to 19 tons of CO2. That is a reduction of 65% of the total emissions of the building compared to the baseline situation. This also represents an estimate energy cost of 2,700 euros per year for the building. Thank you.
Thank you very much, Cristina. Well, very good result, no? More than expecting, so perfect. We have a question for you, Cristina. Thomas Mo is asking in the chat if you use the photovoltaic panels in summer also for cooling or storage during night. You can read the question as well in the chat.
Yes, this was one of the important points to decide this last configuration. So with these panels, we can fit the air source heat pump, and this provides both heating and cooling for the building.
Very good. Thank you so much. So there's no more question for now. So now we give the floor to Gerard Riba. He's the head of urban maintenance of Sant Cugat del Vallès, and he's going to tell us about the Sant Cugat pilot. Hello, Gerard. You have your microphone off, I think.
I'm sorry. Can you hear me now? I couldn't find because I was sharing my screen and I couldn't find the micro button to switch on. Okay. So hello everyone. Thank you, Ariadna, for introducing me. I'm Gerard Riba. I'm the head of the urban maintenance in Sant Cugat City Hall, and it's a pleasure for me to present you the pilot we implemented in Sant Cugat. I think it's very interesting, and some of the results for sure will be very curious and interesting for you. just to know how is our site, we decided to use a site, an existing site, an existing building. It was an sports center. Why we chose this site at the beginning of the project was because we saw that it had a high, heterogeneous, and easily foreseen energy demand along the year. So it was easy to predict how its behavior along the year. Those allow as well to design a large thermal storage tank. So it's our we are the large scale in the CHESERA project, and we want to also to check it was feasible to implement a CHESERA system in an already facilities on service. So it wasn't easy, and it was a challenge for us. I think we did, and we are very glad for that. And more details of the center: it has 3 courts, 3 pools, and several fitness rooms, and obviously the locker rooms for users and an administration and office area. If we talk about energy uses, here in the screen you can see the demand. There is 1 megawatt electrical hour energy for electrical uses and 1.5 in the thermal uses. And this sharing this energy, you can see the more client are the swimming area, because we need around 3/4 of the energy demand is used to acclimatize the area of the pool. Electricity and gas used are supplied from the grid, and there is not renewable energy source on site. So it was a good point to try to do something new here in this sports center. For the CHESERA and proposed for Sant Cugat is what you can see on the screen. We start from the initial state with the 2 existing boilers and the buffer tank. And from there, the production of renewable energy is proposed for 160 unit panels for the hybrid panels, and a solar collection area 264 square meters. Here you see the performance of these panels. Maybe if you use an ordinary panel, you can reach a higher performance, but not so big. And I think it's interesting for us, and it was an innovative solution. And of course, the European Commission adopted that idea to use the EV panel, because it was time to check this product in the market, and if it's possible, and for sure we will promote this kind of innovative solutions. All the electrical energy produced fit into the electrical installation for the sports centers, while the thermal energy produced is accumulated to the test. It's a 100 square meter test in the underground floor of the sports center. And the system works when the temperature of the tank gets the set value of the system, and then the boilers switch off, and the system starts to produce the energy needs to heat the water of the large pool. Of course, we don't get this temperature. The CHESERA system switch off and start to back up with the boilers. What we expected, the estimated results in the designing phase was we did several simulations, and of course the economical and physical constraints were the key factors to decide with the best solution. Finally, our proposal was to achieve a reasonable energy saving. We were talking about 50% of swimming pools annual demand to cover 100% on summer. Energy savings, 187 megawatt hour years in thermal energy, and electrical 60 megawatt hour. The performance of the COP was supposed 5.6, saving CO2 saving was 65 tons, and we expect to reduce our bill energy bill with 21,000 savings euros. After that, of course, after the design phase, started the construction phase. Well, I can tell you that it was a big challenge of the project. It's not easy to build this test in an existing building. I don't want to talk a lot about that, but I think it's important to be mentioned. But everyone to want to a pilot like that to take in account that it is a complex process, and easily it can be longer on time, and of course on the budget of the project. There was three hot spots in this construction was the roof, the test site, the test site, and the pump room site. And just to give you some idea that how difficult can be all of these things. In the roof, for example, we drilled 800 holes, so maybe it was a small holes, but we were really afraid about the consequence of this hole because easily we can get leaks on the ceiling, and after 1 year to finish the project, we have no complaints about that. So we are happy that everything was okay and it's working now. And the test site, of course, you can imagine how can you build a 100 square meters, cubic meters tank in an underground floor. It's not easy. More if you find, for example, an asbestos pipe in the basement where you want to do the basement of the tank. So it was a non-forcing pipe, and it takes longer to the project because we want to be more safety for the workers and to change to redesign the basement of the tank. As well, how to build it. We built it in a workshop. They did pieces of a ring 2 meters long and 1.5 wide of stainless steel, and we bring to the side from a big window where we should to remove. We had to demolish the corners of the corridors. We should to remove as well an stairs just to get all the pieces, the big pieces you can see in these pictures, to the side of the test. Of course, it's easy to say you can build in another place more easily, but of course it's not easy to find a place. The place we found, you can see in this picture, is a wide and long corridor and a space and enough space to house the tank and as well to leave a safety path for people. Okay, we did. We get the rings on the side and we start to assemble, and we insulate with a rock wool, and we close it with a removable panels, easy to remove because for maintenance operation it was more easy. Otherwise, it was impossible to get all the places of the tank. The last one was the pump room, not because it was critical in the process, just because it was the place, an important place as well, where we install all the electrical and hydraulics elements of the system. Of course, the heat pump, you can hear. The result after 7 months, in September 2019, we finished the works. The system was start to in operation, and since that, the startup monitoring phase has begun. We have checked some results, but unfortunately, because the lockdown COVID, from April 20 to July 20, the sports center was closed. This didn't allow us to get the real values. We had to estimate those values. You can see here in shadow, those are the value estimated, but the rest of the value was before the lockdown. So those are real value that help us to know how it's working, at least on winter season. It wasn't what we decided at the beginning, because of course on summer season is when it's more performance of the system and we will produce more energy. But that's what we had, and we are still learning how it's working now. Combining those values, the estimated values and the real values we got, we have the savings expected 224 megawatts hour and 14.5 thousand euros, and 61 reduction of savings of the greenhouse emissions. Another targets, objectives we have with different targets was the contribution of the storage tank to the swimming, to the demand, the thermal energy demand of the swim. We expected that 50% at the beginning we will simulate, but we saw on winter season we are covering 42% of the total energy demand. So that's the worst period on winter. So in summer, we expected more at least arrive to 100%, well, how we expected. And in fact, we checked these values in June, July, and August, and we are accomplishing these values. So we are happy with that. In total, we expect to supply 64% of the energy demand to heat the swimming pool. The electrical production, it hasn't been as we expected at the beginning, but we had several problems. The first one, we couldn't monitorize all the months of the year, just 4. You can see here in this figure the electrical production, and that was because we had different failures of the system, and we couldn't first of all to know the real values, and secondly to check how capable was the system. What important data we can get from here at the beginning is that in the yellow line, can you see the yellow line, the production of the system in the peak hour, it's higher. It's higher in the main hours of the system so we can reduce the peak electrical demand of the sports center. Another important thing that we saw was there are 2 inverters in the installation, and one is producing 20% or 30% more than the other. So and it has no sense because they are likely twins installation. So we both should produce the same energy. So we expect that we are finding what is happening with installation, but it's easy to know that to check that to rise plus 70% of the energy production is feasible. About greenhouse emissions, I told we were talking about before. We reduced 61. We have a saving 61 tons. That is represent a 10%, around 10% of the total sport gas emissions. So it's an important value to be noted. And the performance of the system, we checked 2 things. First one, we were wrong at the beginning because we wanted our simulation, our estimated value was talking about the performance of the heat pump, the cup of the pump, the heat pump. And finally, we have evaluated, monitored only the cup, the performance of the total system. You see here in this table, we go from 3.8 on January until 5.2 on October. There's a correlation between this cup, how big is in October, in concordance with the temperature of the outside temperature of the test. So we have any information on summer. You are just keeping now information, but you know the COVID situation. There is not only people is using the sports center as before. So this data is still too early to say that it's a real good data, but we start to have some information about that, how the importance of the temperature of the system to improve the performance. Just summarizing these values, the Chesserat contribution, the target was accomplished, as well as thermal energy demand. Not the electrical energy saving, because the reason I told you before is we had different values, and of course we couldn't produce all we expected at the beginning, and for sure it can be much more bigger, for sure. I'm sure about that. If you count both things, or for example, if we talk about the performance of the system, we reach in the winter time 4.5. We cannot evaluate with the target at the beginning because we were thinking about the heat pump. It wasn't the value calculated, monitored at the end. And in CO2 gas greenhouse emissions, we almost accomplished the value. We expect that we are very. We think. I think personally we can reach this value. It's gonna be difficult because I told you. I think this 1 year startup year is not enough to know about the system, and for sure we can achieve the optimal function of the system in the next year, but not now because it's not really working as the beginning before the lockdown COVID. In cost savings, we are far away from what we expected at the beginning, but I think it's important to say what we checked before, that in the peak hourly, we have production a surplus of electrical energy. So we can, it's an idea and a point we have to still working in that to try to improve the saving, the economical savings in a flexibility market, maybe not in Spain, but in another places it's possible. And what's next? What's next in Sant Cugat? First of all, to learn more about the CHESERAP system. We are getting new data. I think we need, I told you, we need 1 year more to know how to find the optimal value. And to check after these values if the system is replicable or scalable. I'm not sure still because it's too early to answer this question, but for sure it's expandable. For that reason, in fact, in the control system that you see here, the Synaptic, CHESERAP has started to collaborate with the Integrity Project. Integrity Project is a sister project for us. You can check in our website, and it tries to, in fact, it tries to give us the solution with the electrical production, because the idea is to integrate the cutting-edge technology, and CHESERAP is cutting-edge technology, and solution in a flexibility market to give the best solution, not only for energy reason, as well for economical reason, and just to keep in all the stakeholders connected to the system. There are 10 pilots in total in the project. Sant Cugat is one of these. And the big goals, the pilot goals, is the overall building energy optimization, to validate the possibility to use in a tertiary building as the sports center, and to check the flexibility participation in the simulated electricity market. So I think it's a new window we have opened, and it gives a more add value to our CHESERAP in Sant Cugat, and I think it is interesting to still working in that point. So thank you for your attention. Of course, if you have any question, it would be a pleasure to answer it.
Thank you very much, Gerard. It was very interesting. As you can see in the chat, we are having a very interesting debate, and some partners are already commenting it, but it's not very specific for Sant Cugat, it's more general. So it's okay with you. You are going to save this comment and challenge for the end. And now we are going to give the floor to Nick Bolton from Electric Corby.
Okay.
Hello,
Thank
Nick.
you.
Yes. Gerard, you have.
Yeah,
oh,
yes, I
perfect.
did. Sorry.
Okay. So can you see my screen?
Yes.
You can. Let's get to the right slide at the beginning. There we go. And if can you still see my screen? Yeah. You see
Yeah.
the full screen now?
It's
Great.
okay.
Thank you. So good morning, everybody, and good to talk to you from the UK. So I'm here to just talk to you about Corby and the pilots that we have here for 26 eco homes as part of this project and our Earth Energy Bank project. My name's Nick Bolton. I'm the co-founder of a community interest company, Electric Corby. I'm the project manager on this particular project. As Luisa says, we've been working on for 4 years now. Seems like longer sometimes, but seems like a blink of an eye at other times. So here, you saw earlier the location of Corby is in around the Midlands. We're about an hour north of London, in the middle of the UK. But we're a part of an old industrial town that's had a lot of regeneration, and the developments that the project is piloted on is a new build area, and it's a large extension to the town of around 5,000 houses. And the project we have is just across the way from where our offices are within this development. This is an old picture now. This is all now built out, and our project is in the middle of it. And you can see here that the overall project is around 47 homes, but that's made up of a range of apartments and other houses. And so our target for this was to build an energy positive eco home community. These homes here aren't included in the project. The balance are, so 26 houses altogether, in a range of different types, pitch roof and flat roof, 3-bed, 4-bed, some 5-bed homes. And the idea was to create our overall as a project area. We're looking at community energy sharing and so on across it as well. But very particularly, we wanted to try and achieve an energy positive home. So each home generated at least as much energy as it needed, if not a little bit more, that it could then share with its community around it. So that was our ambition, and the CHESS project came along just at the right time to share that ambition, particularly obviously on the heat generation and the heat storage part of that project, because we were already looking at PVT panels in the scheme. So a little bit different to both of the other two projects in terms of we're a new build rather than a retrofit, and we're also how we're storing the energy is different as well. So we have PVT solar panels on the roof of each of the homes, generating electricity and heat, as you know. We are immediately taking that heat and storing it in the foundations of the home in a matrix of shallow boreholes within the foundations. And then when the home needs to draw on a heat source, we have a ground source heat pump within the home that then draws on that reservoir of heat to heat the home. The important thing, and this is another representation of that system. The important thing to understand is that the temperature of the heat in the ground is obviously relatively low. It's taking a ground temperature normally around 4 to 7 degrees centigrade, and it's raising that up to around 18 to 20 degrees centigrade. But that obviously is the key difference to make the heat pump that bit more efficient, drawing on a higher heat source throughout the winter period in particular. So we're taking summer heat and storing it in the foundations for the winter, essentially. We have monitoring installed throughout the ground source as well. So as well as the normal temperature taken in and out of the reservoir, we had some other monitors that aren't necessary for the operation, but for the research project, put into the foundations at lower levels. They are one of the lessons learned rather that I'll pick up on a little bit later. And the system here it's based on not a bespoke heat pump. Sorry about that, Neil. But we have a commercially available heat pumps in each home, a 7 kilowatt heat pump with its own storage tank within it as well, produced by Mastertherm. We have the PVT panels that you can see, and here the representation of the Earth Energy Bank as well. The other element, just for interest purposes, and it does affect the overall energy management of the homes, we have had a battery system and a home energy system installed in all the homes. So an electrical battery of 5.5 kilowatts taking excess electricity as well. So again, we can transfer from peak generation to peak demand so these are the core element of the homes that were completed for the project. You can see this is still under construction, and the rest of the homes following on round the site. And these are the 3-bedroom flat roof homes with the normal conventional PV mixed with a range of PVT panels as well, to get the right balance of energy generation to match what we believe the consumption in the home was going to be. I'm hoping this is going to work because this shows us on site and some of the challenges on site. We've employed a modern method of construction, a modular approach to construction, both for to improve the construction process, but also to massively improve the thermal efficiency of the homes. You will see in the background very traditional UK built brick homes, which are not traditionally very thermally efficient. So we've employed a system which is way more so. Now, please tell me that's working. It is working. So you can see that it's basically, anybody who knows Lego, it's like putting up Lego. So, but each time the panels are slotted together, they become airtight and watertight. So we have massively thermally efficient homes with air tightness levels that are barely 10% of what they are on the homes behind it. So there we go. So that's, unfortunately, we don't quite build them this quickly in real life, but and we have had some challenges on this new build site. So one of the lessons learned that I'll touch on later is about how we incorporate an R&D project in the middle of a commercial construction project, and that has presented some of its challenges for us. Oh, hang on, let me move on slide. There we go. So so this is some of the images as the projects move forward. You can see here just an image of the Earth Energy Bank. It is a very, very simple system. It essentially involves an excavator with a post drill on it, which drills a series of 1.5 meter boreholes, and then we have PE pipe joining up with glycol in that's then buried underneath insulation and the foundations of the home, and that becomes the thermal energy store. Simple technology, keeping it simple because obviously it's buried within under the home. We don't want things going wrong once it's installed. You can see here PVT panels again on the roof. This is the installation. In this case, it's in a garage within the home where all three elements of the system, the heat pump here, an MVHR, so mechanical ventilation and heat recovery system, and the battery SHEM system all in together. In the other normal homes with pitch roofs, the heat pump remains in room the size of a freezer. The other elements go into the loft, into the roof space of the home. So it takes up limited space, hardly notice that it's there in the kitchens that we have. And I'm hoping that this is going to work. So I'll just show you, we've tried to employ, as we were building the home, some sort of modern technologies to sort of check that the system was deployed correctly. So you can see this is during the construction period, and some of the team from Chess were able to come in at the time and see the installation going in. So you can see the underfloor heating system here. I'm hoping that people can see me. By the way, I'm talking away, and hope they can. This is coming through as well. This point here is a key bit. This is where the Earth Energy Bank comes. The pipe comes down from the PVT at the roof, come down and feeds straight into the ground, and then it's drawn back up and into the heat pump system with expansion tanks here to control flows and so on. This is prior to commissioning, but I just wanted to show that it's all contained in one corner of the garage as a system. I'm hoping I can switch back. There we go. So I'm going to jump straight to how this really has performed, because we've had a pretty good outcome in most respects. So we've got in pretty much all cases, we've had our outputs have been very close to our intended. The COP on the heat pump was slightly less than we hoped for. In fact, our target simulation was still less than we'd aimed for. We did have a target in our minds of 4 on the COP, and we're still working on why we think we've fallen short on the COP. at the moment. So there's a number of theories that we're still working through with the data towards the end of the project to work that one through. But in most respects, we've achieved the targets that we aim for in terms of significant CO2 saving, significant electrical reduction in consumption, down by nearly, well, our target was around 60%. We've got close to 57% reduction. So in terms of our target for achieving an energy positive home, we feel we're getting very close to that. We haven't quite achieved energy positive, but as you can see from the energy results here, a very significant reduction in greenhouse gas emissions from the home, and a total reduction in gas consumption, obviously, and quite a reduction in overall energy use. So what it means is, with the electrical generation that we're able to store, so the home is optimized to use that electrical energy if it's available, or store it if demand is there, or store it if that demand isn't there. So that allows us to optimize the energy consumption as well. And so we have a minimal electrical consumption across the year, and a bill, a utility bill for the end resident of around about 150 euros per year. And in the UK, it's one of those homes you saw in the background in that video image. Typical home there would be around 12 to 1400 euros a year. So it's about 10% of what it would normally be in these homes. We have learned a lot. We have a lot of positive outcomes, but we've also learned challenging lessons through the process. We've got close to our energy positive living ambitions. We've hugely reduced the energy bills that can be achieved in a normal home, and that's great for the people that are moving into the homes. Seasonal heat storage obviously is a key part of that, achieving that energy positivity, but it is a complex system, and in a home, it's particularly challenging. The patterns of usage aren't quite so predictable. Integration of the system shouldn't be underestimated, I would say, and I think that has probably been our single biggest challenge, with all of those different elements, including bringing battery storage into the equation and making sure that that was working optimally with the system. That has been something of a challenge for us as a team. And as I said, incorporating R&D projects in a live commercial housing scheme brings many challenges. A variety of contractors, not all of whom are working to the same objectives as the R&D project. You also have commercial pressures on a scheme going through a 4-year period. A lot can change. A lot has changed. As the next point, and others colleagues have mentioned, the challenges of COVID have impacted on the project, in particular the rate at which the homes have been occupied, because just at the point the majority were ready to be occupied, we weren't able to move people in. So we had some homes occupied, enough to provide our monitoring data, but not as many as we hope to have, to give us a broader view on how these homes would operate. I think stability and security has definitely been a challenge for us, and it's had a knock-on effect and challenge for our colleagues in the project. Again, a combination of factors, with a commercial building site, with relying on external parties, with finding reliable backup systems when main systems were not working. All of those things have been lessons that we've learned to, and have had some impact on the data we've been able to gather. I think part of there is a risk in these situations of over-engineering solutions, because we've built an extremely efficient home in the first place, and we've created and engineered a solution that we think in hindsight has the potential to overachieve for the home, and certainly at certain peak times we think the system is maybe more complex than it ultimately needs to be. If we were doing a next version of a home, in fact we are already planning this, a simplification of parts of the system, is what we'd like to do. And at the end, we do have, importantly, an attractive business model for our partners. Not different partners have different expectations, so our technology partners are already taking the system in its simplified form out to new homes and talking with other developers. We haven't yet adopted an ESCO approach, but we are in discussion, and I think what I was going to show as a final slide is this is our sort of next planned community, which would involve and present the opportunity for an ESCO where we have shared a further level of sharing going on in a rental accommodation, allowing us to share the energy across all the different homes, as well as having shared energy into electric bikes and electric cars. So that's where we're looking to take the learning from this project and the business model on both the technical solutions and the ESCO model into the next project. So that's a commercial project rather than an R&D project that we're looking to take forward. So that was our experience in Corby. Thank you very much, and I'm happy to answer questions now or later or online. In fact, I think I said at the beginning, if anybody wishes, yes, my email address if anybody wants to get in touch. Thank you very much.
Thank you very much, Nate. Very good summary of the lessons and the outcomes. Thank you for keeping us in time. We're going to give now the floor to the part of capitalization and transferability of the project. First, we have Jordi Ferrer from Watia, who will tell us about the control and monitoring system. Here you go, Jordi.
Okay, do you hear me?
Yes, Jordi, we can hear you.
Yes, okay. Do you see my screen? Okay.
Yes.
Okay, good morning to everybody. My name is Jordi Ferrer, and I'm the head of the IT and R&D department at Watia. Watia Innova is a company mostly dedicated to the engineering, control, and automation in homes and buildings. And we are always focused in the energy efficiency, not only switching off on and off lights and curtains up and down, but we also like always to control the energy production and distribution in homes and buildings. And in the CHESS Setup project, we are the partner responsible of the design and implementation of the control and monitoring tool. So in the presentation, I will describe and show results of this software. Oops, next, okay. So I will start with a brief description of the CHESS Setup system, for which we designed and implemented the control and monitoring tool. I will describe the key points we took into consideration for design and the implementation of the control and monitoring tool and the features we wanted to implement. Then I will make a brief description of the implementation. And if everything works fine, I will try to show you an online demonstration by connecting to one of the pilots. And finally, I will describe the ongoing and future work, which is basically a collaboration to another Horizon 2020 project. Okay, so the CHESS Setup system consists basically in a seasonal thermal energy storage tank here in the bottom left corner. Then we have a set of hybrid solar collectors, the PVT panels, which provide both electrical and thermal energy from the sun. We also have here the customer that has heating or domestic hot water needs. And then we also have a heat pump here in the middle that is used in the case of needed to raise the temperature of the energy stored in the stress tank. So basically the control system has to store energy in the stress tank. The control and monitoring system has also to provide energy to the customer from a buffer tank. And in the case if it is needed, there is also typically a backup heating system, which is normally a gas boiler. The control system has to provide the energy directly from the test to the buffer tank, if it is possible. This normally depends on the temperatures that the customer requires and the temperature the seasonal storage tank has. If it is not possible to deliver the energy directly to the customer, then we use a heat pump to raise the temperature to the set point the customer needs. There is also the possibility of delivering energy directly from the PVTs to the customer, but it is a very inefficient way because the production and the consumption curves doesn't match. So it's only considered in the case there is, for example, a failure in the heat pump or some problem in the storage in the test tank. Then we basically designed and implemented a control system that solves this problem and works autonomously. During the design, we decided that it is very important that the resulting system is very robust. The heating of a building is not a matter of life or death, but the chest setup is typically designed for large customers, so there might be many people depending on this system. So we wanted to make it as robust as possible, and basically the main functionality, that is storing and delivering energy to the customer, never stops. Then in our experience, in many projects, the first solution always grow along the time. So we wanted to design a system that could grow if it is needed. I mean, add more customers or more storage, more PVT panels, another heat pump or whatever. So we need a solid base that allows more hardware and software to be developed. We also rely always in the usage of standards in the buses, communication protocols, programming languages. This allows us to communicate practically with any device of any brand in the market. We also wanted to have a visual interface usable for the different users. Typically, we have the viewers and the operators. The viewers can see what is happening in the system, while the operators can change, for instance, the temperature set points or other parameters in the system. And in our experience in the world of home and building automation, we know that it's very important to have a data storage, because typically you get questions of what happened at a particular moment in time. So if you don't have this register, then you are not able to answer. And actually, it's also very useful to detect possible problems or hardware or software errors. Moreover, here in the chest setup, we need to generate reports of the resulting implementation, so the data storage is mandatory. Then the system has a visual interface for the users, and using this visual interface, one can generate plots and trends of whatever there is in the system. So sensors, actuators, the power, energy, whatever is registered in the system. The tool implements some of what we believe that are the important plots, but it always happens that some users want to see other or different plots. So we want also the data exportation option in order to provide the users the data stored in the system in a standard format. And finally, we also want to implement or design and implement an alarm system to send, for instance, emails to the operators on predefined events that might need some actuation in the system. And finally, since it is an European project, so it doesn't hurt if in the final implementation we add a multilingual functionality, so we can set up the final system in many languages. Okay, so then we decided to implement the system as robust as possible. So we defined two different layers: what we call the low the low-level control and monitoring, which is basically this in here the layer in green, and it is based in a PLC controller directly connected to the hardware. We have many of these controllers that have been working for more than 15 years without any issue. So it's designed very robust. And if anything fails on top of this layer, so if anything fails in here, the system will keep working, and a program can still connect directly to the controller to perform whatever modification, start, stop, or modify whatever. And on top of this layer, we define what we call the high-level control and monitoring, which is the layer that has a data storage, the database interface, and the SCADA tool that will use the operators of the system. This layer runs on top of a PC computer, and has software designed and implemented by us on the SCADA tool and on the database interface and in the operating system. So typically here, the operators of the system connect directly to the system through the SCADA, directly or locally or remotely. So in here, the scalability, connectivity, and the standard usage is done in the two layers, but the low-level layer gives us the robustness, while the high-level control and monitoring system layer provides us all the other points we define in the design. Obviously, the control system has to satisfy the basic functionalities we already described: the basic control, the energy, the storage of energy from the PPTs to the stairs, the delivery of the energy to the customer, either directly or through the heat pump, the basic visualization, the data storage. But we added some extra features that, in our experience, are very helpful. For instance, we added an anti-freezing algorithm in the PVT panel's primary circuit, because typically this circuit has glycol to prevent the freezing, but we know that along the time the people refills this circuit with waters, then the concentration of glycol might decrease, and maybe the operator is not aware of that. So the system has an anti-freezing protection algorithm, which is basically a recirculation of the water depending on the outside temperatures, to avoid the freezing of the pipes, and that could damage them or damage another device. And also, we minimize the hardware wear out. For example, there is critical parts of the circuits where there are twin water pumps. There is the main one and the backup one. In the case of the main one fails. So the system automatically takes care of alternating the usage of the heat pumps to keep them identically used. This way, we don't use always just a single one, so that when we need the backup one, it doesn't work because it is rusty or stuck for not being used for a long period of time. Then the system is also designed and implemented to maximize the performance by delivering the energy directly from the stairs tank whenever is possible, and using the heat pump only when it is required. It also works at the lowest temperature possible in the PVTs, in order to maximize the electrical performance and minimize the thermal losses. So for instance, if the stairs is at 15 degrees, we keep the PVTs, the PVT production at, for instance, delta T of 5 degrees above this temperature, so at 20 degrees. If the stairs is at 30, we will operate the PVTs at 35. And finally, the system also provides the basic plots from sensors or energies, but also higher level information, such as the overall system COP, or for example, the thermal and electrical savings, or the PVT performance. here I will show you the low-level implementation, which is based on a PLC controller that has input-output modules connected directly to the controller. So there is nothing in the middle that could fail. And then the sensors are directly connected to these modules. For example, we have these RTD modules where we connect the temperature sensors, and we have digital inputs where we connect the bulbs to know the state, open or closed, for instance, and digital outputs to operate the digital bulbs or the water pumps, and analog outputs, for example, to connect to the proportional valves. The less robust, let's say, the less robust weakest point in terms of robustness is this connection, sometimes due to the distance requirements. You need to wire a remote heater through an Ethernet connection. Because the hardware is very far away from the controller. And in this case, the Ethernet connection is the weakest point. However, you can set up a point-to-point or a dedicated Ethernet segment to this connection to keep the robustness. And the high-level control and monitoring implementation is PC-based. So we have a industrial PC computer with an operative system. And on top of it, we install a database engine, an open database engine such as MariaDB or MySQL, and a SCADA tool. And this SCADA tool can connect to many of the devices we have in the system. So for instance, the calorimeters, the energy meters, the heat pump, the PV inverter, and also to the low-level controller to share read and write data. And the SCADA controller can also connect to the internet to obtain other information. In that case, we get the energy prices to calculate the electricity energy savings. And the operators can connect to the system remotely or locally. And so finally, we have an implementation that has been done during the project and tested in the pilots that solves the chess setup, control and monitoring problem and implements the described key points and features. It is easy to use for the viewers and the operators of the system and can easily be replicated and adapted for different hardware since we use standard protocols and systems. The tool we developed doesn't depend on any size of the stairs, PVTs, number of inverters or heat pumps. It can easily be adapted, and it helps in the assessment of the system. So we generated the project reports of the project using the data coming from the tool, and we also used the tool to detect some problems in the pilots. For instance, we had in one of the pilots we had water leaks in the PVT primary circuit, and also we detected that one inverter is, for instance, producing less energy than the other. So there might be a problem. And now, if it is possible, I will try to connect one of the pilots to see how it looks like. Do you see this screen?
Yes.
Yes.
Yes. So this is a connection to the chess setup, or remote connection to the chess setup implementation in the Sant Cugat pilot. And here we have the layout of the system. Here we can see that today it's cloudy in Sant Cugat, right, Gerard? And
yes, it is. It's cloudy.
Yeah.
I can take a picture if you want.
There is a very low radiance and a very low production. And we see here there is nothing highlighted, so it means that there is no production. And we here see the test temperatures, 43 degrees, and we can only reach up to 27 here in the PVT panel, so there is no production. We also see here the customer, which is a pool in that case. This is the pipe coming from the pool. So the pool is at 29.8 degrees. Now I will try, if it is possible, to change the set point. Here we have the configuration for different subcircuits of the system. Here it's the set point of the pool, which is 30 degrees. And now it's at 29.8. So this means that it is about to start, because it starts at 3/10 below the set point. So it's practically about to start. I will try to force it. I'm logged in as a viewer, so I cannot change it. So first of all, I have to change to operator. So if I set here 29.8, the system should start trying to provide energy to the pool. So now the system is at waiting, so it's not providing energy, but now it should start to provide energy to the pool. And since the temperature in the stairs is much higher than the current temperature of the pool, so it will be delivered directly to the pool without using the heat pump. So while this starts, I will show you, for example, here in the plots, we can try to do a COP plot. For instance, we choose from just when we started up to now, and by month. So this is the COP of every month since when we started the pilot. This is 47. This is the overall COP, so it's the whole electrical consumption against the thermal production. So it's 47. So in here we didn't use the heat pump at all, so we were providing energy directly to the stairs. So that's why the COP is very high. While in here it's a little bit lower. I think the overall COP is around 6. I think this is the number that Gerald already showed. So it was not the COP of the heat pump, it's the COP of the whole system.
5.2 in October it was.
Okay. So I did something wrong because...
Excuse me, Jordi, just a friendly reminder that we are delaying ourselves a bit. So if you can finish in 2 minutes, it will be great.
Yeah.
Thank you.
Yeah. Sorry. Well, so this is the tool and so in the ongoing and future work, so we got some time ago, Sant Cugat and us, we got connected by one of the partners of another Horizon 2020 project, which is called Integrity. And they asked, so they had some issue, I don't remember well, but they had some issue with their own pilot, and they asked us to use the Sant Cugat's Chess setup implementation as a pilot for their project. So we divided this collaboration in 3 phases. And the first phase, we will write an API, a piece of software, to allow them to extract information from the Sant Cugat's pilot, and also to allow them to remotely operate the system. Then in the next phase, we will integrate an air conditioning system. So we will measure the consumption and thermal production of this system, and we will also integrate another PV plant. And in the third phase, sorry, and then we will, in the third phase, we will integrate a dehumidifier. So we will control and monitor this system. So basically, we are going to write a piece of software here, which will allow the integrated project to connect to the Chesed app remotely, and then the installers will add some more hardware, and we will have to do some more software for doing the integration in here in the database interface and the SCADA tool, and also maybe in the controller, in the low-level controller. And that's all.
Thank you very much, Jordi. Well, very interesting. That's a very important part for the Chesed app project. So we have to keep us at the time. So I will ask the next speakers if they can adjust their schedule to 5 minutes, please, or more or less. Thank you. We have now Sergio from Barcelona Ecologia, who is going to explain us the simulation software of Chesed app. It's a very useful tool, so go ahead. Thank you.
Okay, thank you. Can you see my screen?
Yes.
Okay. I am Sergio Sanchez. I am a team member of the Urban Ecology Agency of Barcelona. I will introduce the Chesed app simulation software. The simulation software is a free tool and can be used by end users or other projects. The main objective is that you can have an overview of how it works the system and the result that can be obtained for the simulations. As could be seen in the previous presentation, the Chesed app system is composed by a sort of elements such as solar panel, the seasonal storage tank, and others. And these elements interact with each other. This software intended to carry out a preliminary system sizing quickly and simply to have an idea of the Chesed app system performance, and also execute an economic analysis that shows the investment cost, economic savings, and the investment recovery. To analyze the feasibility of the proposed system and calculate the result, it's necessary to perform a simulation of mass and energy balance between the different components. The simulation software performs an early simulation of all the system components during a 2-year period. But how the software works? The software is composed of 4 modules. The visual interface. This module is composed by the input data, the weather data, the energy demand, and all the technical parameters of the system, and the output data that is the energy performance, the equipment efficiency, the economic balance, among others. The second module are the libraries. The software requires some precise data, such as the hourly meteorological data, the hourly energy demand, and the technical parameters of the equipment. In order to simplify this task, there are available several libraries in the software. Another module is the project database module. The software includes some reference projects and others that can be uploaded by the user. And the last one is the data process and calculations that contain all the formulas and programming that perform the calculation, and these modules are not accessible by the user. To start a new project, we must enter the input data for this data, and remember that our libraries and pop-up information to help you in filling the data. In this slide, I explain how to define your project. We start with the location or place of the project and the climate conditions. The software requires early data about weather conditions. As I said, to simplify these tasks, the software includes libraries with weather conditions for some European capitals representing the main climate region, like Berlin, Amsterdam, Bucharest, Madrid, among others. Another option is to add a new location and add their climate. You have to define the climate condition, the solar radiation, the air temperature, the ground temperature, and the irradiation. Sorry. For example, solar radiation data will be directly related to solar panels energy production. The solar radiation in your location can be obtained from PVGs. The solar radiation is based on early data inputs with defined average values for daily basis. Afterward, monthly values will be generated by the software automatically. The same should be done for the air temperature, the ground temperature, and the radiation. Now, in this step, the building energy demand has to be defined. The energy demand is related to the building type and also is related to the climate condition of the location. First of all, you need to select the type of building you are working with, which will have a temporal distribution of the energy demand defined. The software includes libraries with main building typologies, for example, hospital, hotel, single and multifamily housing, sports centers, among others. Afterward, the total annual energy demand has to be defined. In this example, for a sports center located in Barcelona, we have heating and hot water demand. Finally, you also have to define the water supply temperature. Each of the building typologies included in the library has reference values for energy demand, temporal distribution, monthly and daily distribution. For the hot water demand, there are already libraries with reference values related to the typology. In this case, for the sports center located in Barcelona, the months of greatest demand are January, October, and December that are related to the weather conditions. And the hours of greatest consumption are from 7 p.m. to 10 p.m. They are related to the use of the building. Okay, now in this section, step by step, we have to define all the setup system components. The solar panel, the seasonal thermal energy storage, the heat pump, the direct use tank, the distribution system, and the auxiliary energy system. For the case that we see now, the solar panel, the simulation software includes 3 different options: vacuum tube panels, flat panel, and hybrid solar panels. The input to be defined by the user are the inclination, azimuth, and solar surface. For each type of panel, the software has some reference values of their performance and recommended operations temperature. Now we see the seasonal thermal storage tank. There are 4 types available in the software: tank thermal energy storage, borehole thermal energy storage, pit thermal energy storage, and aquifer thermal energy storage. There are some reference value already defined for the storage system and the storage material selected, but they can be modified. The values to be entered are the tank's volume, the surface, the maximum and minimum temperature. For the heat pump, there is one model already defined, the chest setup model. The heat pump power has to be defined for this component. At the same time, there is option to define a specific heat pump for your project. You will need to fill in every blank, and in case you require some information or assistance, there are some pop-ups information. The same we have to do with the direct use tank. We have to introduce the inputs to define it, the tank's volume, the surface, the maximum and minimum temperatures. Also with the distribution system, we have the system is composed of 2 stretches, from the solar panel to the storage system and from the storage system to the demand side. The inputs to be defined are the length, diameter, insulation width, and thermal conductivity. Finally, we have to define the auxiliary energy system. A backup system may be required to achieve the energy demand when there is no available energy in the seasonal storage tank. Some options are electric resistance, gas boiler, biomass boilers, among others. Once we are defined all the components of the CHESETA system, we have to introduce the economic data. The economic data section provides information about the initial investment and the yearly operational and maintenance cost for each of the system components. The software has also some reference values. The price of energy supplies will be also defined in these sections. Once all the system components are defined and the economic data are filled, the software is ready to simulate. And after running the simulation, a screen with the main output of the software will appear. In this case, in the left figure, it can be seen the contribution in percentage of each of the different components. In blue, the energy supplied by the heat pump. In green, the solar contribution. And in pink, the auxiliary energy system. In this case, natural gas boiler contribution. In the right figure, it can be seen the energy balance of the system. At the bottom also, it can be seen the overall result of the system implementations. Some relevant values are the self-sufficiency of the system, the energy consumption saved, the emission saved, the payback, the investment, operational, and maintenance costs, among others. Continuing with the overall result of the system, an analysis of a system component is also present, where it can be seen the thermal and electrical production of the solar panel, the heat pump electrical consumption, and the yearly COP, the energy consumption of the auxiliary energy system, the temperature of the thermal storage tank, and the thermal losses. In this slide, the figures above show the monthly energy demand of the system. In blue, the building total thermal demand. In green, the energy consumed by the auxiliary energy system. In this case, the gas boiler. In red, the solar contribution. And in pink, the energy consumed by the heat pump. Finally, the figure below shows the hourly average temperature in the two tanks for a period of 1 year. The red line corresponds to the seasonal energy storage tank temperature. It can be seen how during the month of higher radiation and lower thermal demand, the heat is accumulated in the tank. And the blue line corresponds to the direct use tank temperature. As it can be seen, the temperatures remain between 40 and 55 degrees. This was a very quick overview of the CHESETA simulation software. I invite you to use the software as a quick and simple tool to obtain a preliminary sizing of the CHESETA system, where a quick assessment based on energy, economic, and environmental performance can be made with it. Remember that it's a free tool that can be used by end user as well as by other projects. And to make an executive and definitive sizing of the system, more precise software like Transys must be used to sizing the project. Thank you for your attention.
Thank you very much, Sergio. You have the presentation, so you have the link for the software, and you're very welcome to use it. Now we are a little delayed. We have 5 minutes and we have 2 speakers. But so I give the floor to Josep Mitaps from Veolia. Please, Josep, can you touch to 5 minutes? It will be great. Thank you very much. We don't hear you.
Hello, can you hear me?
Yes, now yes. Thank you.
Okay, perfect. Well, thank you very much for your presentations. I will try to stick to my 5 minutes time slot as much as I can. Well, my name is Josep Mitats. I work in behalf of Veolia, and I will try to summarize as much as I can, which is the main character of the energy service and the ESCO business model that we applied here, and not only in Veolia, but specifically for the case of the CESETAP project. Well, first of all, I wanted to highlight the definition that you can find in the Energy Efficiency Directive of the European Commission, which is an energy service is like physical benefit, utility, or good derived from a combination of energy with energy efficient technology or with action. It may include obviously operation, maintenance, and control tasks, which are necessary to deliver this service, which is delivered to the basis of a contract and in a normal circumstances has proven to result in a verifiable and measurable or estimable energy efficiency improvement or primary energy savings. So in fact, an energy service company is, as also stated in the Energy Efficiency Directive, is this natural or legal person, usually in the form obviously of a firm or company with a high level structure, who delivers energy services or other energy efficiency improvement measures to a final customer's facility or premises. And as it's widely known, the remuneration of ESCO is directly tied to the energy savings achieved and as stated in the contract. And the ESCOs can finance or assist in arranging financing for the operation of an energy system by providing a savings guarantee. Some of the main energy services can be seen in this figure, which is, for example, the energy supply contracting, energy performance contracting, which I'll be speaking of right now, energy consultants, energy management system, etc. So how do we offer those energy services? Well, for example, here in Veolia and specifically in Spain, as we are deeply inside the energy services market, we based our energy services provision in a kind of development that the Instituto para la Diversificación y Ahorro de la Energía developed right in 2007, and that has been obviously developed and enhanced over the last years. It counts on 5 main provisions, which can be seen as it follows. Provision 1 is energy management, performing all energy management tasks, supplying warranties in terms of quality, quantity, safety, and lowering purchase costs via different ways of contracts that I'll be explaining later on. Provision 2, which is maintenance, obviously taking into account all normative, corrective, and different maintenance tasks. Same for provision 3, which is a full warranty repair, meaning that whenever any equipment or installation goes wrong or fails, the ESCO is committed to assume all technical and substitutional risks of repairing or even substituting all the equipment or devices deployed. And finally, provision 4 is improvement works and installation and renewal, meaning that the ESCO is going to have a deep market analysis on the main relevant new solutions that could be entering the market, so that can be deployed efficiently and effectively in the customer's facility. So here is one of the main P1 services in terms of how do we expect to perform all those energy services in a contract way. The energy supplying contract is a contract where the energy efficiency measures are being typically limited to the energy supply and transformation side, so that the subject of this contract type is the supply of energy, usually in the form of heat, but it can be obviously in the form of cooling, in the form of electricity, it depends. And as you can see here, the current cost is meant to be here, and obviously we are committed to leverage the estimated energy cost as much as we can, and in some agreed conditions. The energy performance contracting is the structure that we've been following here for the application of the CESETAP project, which is the kind of similar, but in this case, we are paid in relation to a contractual agreed level of energy efficiency improvement or some other energy agreed performance criterion, such as financial savings, obviously, but that can be also extrapolated to some relevant performance of the system. In that case, we have 2 different contracts, which is the guaranteed savings contract. In this contract, the ESCO guarantees at least a minimum savings that will be obtained through implementation of these energy measures, and it receives an amount of money for the incurred costs and the project profitability, of course. And the investments are generally assumed by the client, which I will be later on explaining in terms of the financing schemes and options, while the ESCO assumes the technical risk. So we can see different cases. In case one, for example, the real cost is the same as the estimated one. So the savings provided by the implementation of those measures are fixed through the client. And the same goes for the ESCO, so its expectations are fulfilled. In case 2, we have a bigger current cost than expected. In that case, ESCO should pay for the extra cost. And in case 3, we are even improving our expectations so that these savings can be shared between the ESCO and the client. And in the shared savings contract, the savings are obtained with an implementation of an energy efficiency project are also shared between the client and the ESCO. But in that time, the ESCO also assumes both technical and financial or credit risk of the client, so that as you can see here, the amount of the savings for the client and the savings for the ESCO in terms of backing up or recovering the investments are fixed, and then the savings for the ESCO are limited to the performance that obviously the ESCO has expected. That's another kind of contract. In the case, the forfeit contract is based on an agreed amount of energy consumption, and then the price of this energy supply or this energy management is fixed. And then this price is reviewed annually, according to some variation of these parameters. Obviously, Veolia or every ESCO has its own way of performing this analysis, and with a formula that obviously is established at the beginning of the contract, so there's no problems before that. And as you can see here, I'm not going to extend myself. You can see the same as before, many options or many foreseen possibilities while deploying this contract. In the end, as I was saying, it is not mandatory to implement all 4 provisions. You can choose between them, either if you're only interested in energy management and supply, or even, and it's always happening, or many times as ESCO we're finding out, the clients and customers do rely on ESCOs or professionals in the energy service providing to rely on their preventive and legislative maintenance knowledge. The same goes for the warranty. Everyone wants to be secured in terms of any failures or problems on their equipment and installations. And obviously, everyone wants to be aware of any new developments or researches that are being performed in the energy market. So kind of important to have an investment ready for energy efficiency and new equipment renewals. Well, here it was just a kind of a resume of what we were saying before. In the energy performance contract, they say the guaranteed savings model relies on the client to ask for a bank loan and to gain it through a fixed repayment, and then pays the ESCO based on the obtained savings, etc. The same goes for the shared savings model, which is the ESCO who relies on or who takes on this also this credit risk. And there are also super ESCOs who can offer both. And obviously that depends on the customer preferences and access to the capital. But in the end, a direct loan agreement with a third-party lender is an option for both parties in case that no one wants to really assume this overall financial risk. Well, here it is just a summary of the main ISCO business model benefits. As it's widely known, the externalization of these services results in obviously in a reduction in the energy costs, and obviously in GHG emissions reduction, and obviously that's directly linked to the energy savings. A transparency on energy and operational costs, which is very important for our clients. Minimization of technical and operational risks. It's mainly what the ESCO is taking or assuming. The same for, as I was saying, normative and legal compliance of all activities performed. Obviously, an energy asset optimization with a comprehensive maintenance plan for our clients and customers. The development of a corporate image which is committed to energy efficiency and energy savings, and obviously enhancement and warranty of installation financing options. And just as a brief summary, as you know, we're running out of time. I just wanted to show kind of a Gantt chart that we Veolia have performed and have retrieved to the rest of the consortium as part of our exploitation plan in terms of replicating and maybe escalating the chess setup project solution to other clients. In that case, we based our exploitation plan in 5 main milestones, which is first of all, obviously the benchmarking and KPI analysis of thermal energy storage systems. Then later on, we should have scope for the market targeting and customer segment identification. Then later on, obviously seeing which are the market competitors that could be playing the same role as us in the energy service market. Then later on, contact with the technology providers, manufacturers of the test equipment, so that we can derive it to the purchase department and see if it fits with the financial profitability and so on. And at the end, the replication and an escalation of the test system configuration. And as many of you have already know, thanks to the pilot organizers, we have been deploying all these energy services and maintenance models through all different pilots adapted to each of the realities. And we have seen that this kind of model really fits with what was expected and provided at least the standardized solution to see if this to adapt this business model, the ESCO business model, to each of the pilot sites. And thank you very much for your attention. And if you have obviously some questions, I will be glad to address them. Thank you very much.
Thank you very much, Josep. Very interesting. We don't have questions right now. We want to save it for the end because we are a little delayed. We have one more speaker. I give the floor to the guest speaker. Very interesting one. It's Alejandro Del Amo from Arbora Solar. It's the CEO. So he's going to explain us the transferability to chess setup and adoption in other cases. Alejandro, are you here?
Yes, can you hear me?
Yes.
Yeah, perfect. I'm going to share my screen.
Perfect.
Can you see it?
Yes.
Yes, so first of all, thank you for inviting me to this presentation. I'm very happy because the results and all the information you have shared with us, and it's very interesting, this project. And what I try to explain is how the impact has been in terms of the real market in commercialization, and how these ideas, this concept of installations has been extrapolated to other installations. So first of all, say thanks to Barcelona Ecologia and Ayuntamiento de Sant Cugat, because they have trust in our technology, and has been very important for us to have a first pilot, because this first pilot is the first step to other installation that we are building up or we have already done. So I'm going to show you some real installations and some projects we have done and we are working on. So as a very fast index, I'm going to show you some installation in the industry, in schools, in the university, in hospital, prisons, business centers, blah, blah, blah. So the first one is ARPA, is an industry here in Zaragoza, where we are. So first of all, I have omitted this information, but we are here because we are, our technology has been installed in one of the pilots in chess setup project in Sant Cugat. So that's why our technology is there. So is also implemented in other projects I'm going to show you. Another thing is not only the installations I'm going to show you now very fast. Other 32 projects, new projects, is building up. So it's a very huge impact, this pilot in Sant Cugat for us. So congratulations. This first installation is in the industry sector. There are no heating demand during summer, and that's why seasonal thermal energy storage has been very interesting. And what we have proposed to this industry is to develop a very fast container where the seasonal thermal energy storage can be implemented, and it's very fast to put in installation. So how it works, heat and electricity, because hybrid panel is used in the building. If we cannot provide all the heat required by the building, we use a boiler. In summer, we are using an adsorption machine to cool the office, but also the medium temperature is storage in this container. When in spring and autumn, when the heat demand is 0, we can store this energy, and in the beginning of the winter, we take the heat from the container. We are using a water heat pump to increase the temperature and to provide, because it's an existing installation where high temperature is required. So the whole system seems something like that. So it's not so complex, too many lines, but it's not so complex. Another installation we have already installed and it's working is a British school. There are no heating demand during summer, so we store the energy and we use it in the ventilation system during the winter. This is how the hydraulic scheme seems like. And we have learned a lot of ideas from the Sant Cugat pilot in order to simplify the system. Another project we are working on right now is University of Zaragoza. This building is being building up right now. This is the some render we have had from the architecture. And on the roof, we have 3 different roofs, 2 of them with PVT panels and 1 of them with photovoltaic panels. So our philosophy is, once the heat production, the heat generation is enough to provide 90% of the heat demand of the building, we don't use more PVT panels and we go to PV panels. How the section of the building seems is something like that. Here we have water heat pump, the panels, the heat pumps, and here you have the buffer, 300 cubic meter, okay, that has been reduced to 70 cubic meter because building limitations. Is a pity because the storage in every installation is the component that always is reduced, and I think it's a mistake, but the reality is something like that. And you can see the buffer already installed in the university. So now the building is more higher, but it's not ended. Here you can see some image of the buffer. So another example is the Barbastro Hospital, also with solar thermal energy storage, no cooling system, but thermal energy storage. Here you have the buffer located always in this ground stage. Also, another example we have is San Sebastian Prison. Sorry, because we cannot provide drawings. So, but I can show you some hydraulic scheme. This is a very interesting system because it's a combination between PVT plus heat pump plus solar thermal energy storage plus district heating, because a lot of buildings are connected. So this installation work, here you have the panel, here you have the buffer, and the heat is provided to the grid network, but also for the cooling system. So it's a very, very integrated system. So just setup don't end here, has future. This is a good conclusion. So more detail, you want to see more specific. Also, we have here a Expo Business Center in our city. There has been some buildings are in process of refurbishment, and 2 of them has the same idea. So this is a district heating network, and we implement the solar thermal energy storage on each building separately. So 2 of them is going to be refurbished this year. This is how the hydraulic system is connected. Also, we have a hospital in Badalona. The section is this, something like that. This is the roof. This is where the buffer is located. Another hospital in Aranda de Duero. I want to share you something. When we provide new ideas to the engineer, this engineer has more points to gain tenders, and this is what's happening with our proposals. So all thanks to Chessetup. Some render of the installation and some section how the distribution on the roof is, the auxiliary heat systems, the heat pumps, I mean, and the buffer. So thank you to everybody because we are we say very thanks to you all. And if you need some more information about any project, please, you can write me to my email address and we are open to talk with you. Thanks.
Thank you very much, Alejandro. We are very happy that the concept is expanding toward Spain and other countries, so very good. And now it's time for the question and answer debate part, but unfortunately we are out of time a lot, so we are going to skip this part. We of course have collected all the answers that is in the chat of YouTube and Zoom, and we are going to answer it in the official account of Chessetup personally, or you can contact us by the contact form or the website. And of course, there are also questions in Twitter and LinkedIn, and we are already replying it. So thank you very much. Now we are giving the floor to Alejandro, the other Alejandro, that is going to present us the visual summarize of the conference, and it's going to be the closure of the Chessetup conference. Alejandro, are you here?
Yes, I'm here. So I'm gonna go quickly through the whole wrap-ups. Sorry, I was sometimes when I take notes visually, it's really difficult to get back to the oral language. So my role here is to make a visual wrap-up. So it's a tool that sometimes people use in the conferences to explain, to go for the key elements of the whole conference. So in order to start a debate that unfortunately we don't have time now. So I'm going to share my screen. Okay. Okay, yeah. So here we started, of course, with the welcoming of an opening, of course, of the conference, in which we said we focus on the need of this project within the frame of the target of the EU in the to be climate neutral to 2050. We also describe a little bit in details the Chessetup project that started in 2016 and finished in 2020, with a little bit of a scheme schedule there. So then we moved to the Chessetup overview that we can, I mean, you have all the information there, but it's of course, again, to repeat that we need to we need to reduce this percentage that the EU building sector produce in terms of energy. On the other hand, we run through the different objectives, the consortium, the system, and the different pilots. One of the key messages that came up is that it's easy to adapt for all kind of buildings and all kind of climates and different situations. That has been proved using the different with the pilots that you have impulsed. Then we moved to the advances in the heat pump implementation, especially those linked with housing. And there are too many challenges. One was what is the maximum capacity deliverable from a wide speed unit, one deliver from on the start of the state. So Neil Hewitt just responded to these two questions. And basically what he focused on was that we are moving towards new advances in this heat up pump, so that we in the projects. And we moved to the pilot experiences. One was Lavola, that used photovoltaic panels and Airsource heat pump, buffer tank, and thermal storage. That the main key elements that they mentioned is that there's no thermal energy wasted, and the surplus is is probably to the electric grid. They avoided to the waste of energy during the summer, so it's kind of a nice outcome. And it's at the headquarters of the company, and it's quite a new. It's a brand new building built. Then Sant Cugat, you have three different, it's another type. It's 3 pools, 1 sports center and administration building. Then they use different elements of the different elements of the system. One of the different key messages that Gerard told to us that they didn't have before energy renewable sources to electricity and heat of the project, that they reduce extremely the energy bill, but they also experienced some construction problems during the period of construction, but also that the estimated values are not real now because of the situation now with the COVID. So they need 1 year more to make to really have real results based on the project. This is one of the projects that is moving forward into integrating the EU projects. That's kind of a community, and there are like 8 countries involved in there. Then we move to Corby. There is also use the heat pump, the solar energy storage, and solar PVT panels. And he highlighted different elements, but the first was that it's an attractive business model to put it on. Then they managed to set it up with simple and effective technology, and also that sometimes they found difficulties to have stable data due to that is taken by someone else's control. Then we move to the capitalization. First was the control monitoring system. That is quite difficult to understand for me, but it was, I think it's because it's too technical. But the key elements is that there are 2 levels of security of this system. That is scalable, replicable, adaptable. That is also can be one of the features is the connectivity that could be remotely or locally. That they have this visual interface and multilingual. The robustness is strong, but at the same time they have different weak points that they are working on. And it was presented by Jordi from Wattia Innova. Then we move to the simulation software. That is a free tool that you can use to help to design your chess project. It calculates the size, the economy benefits based on the different characteristics of the project. And it has different elements: a data process and calculation, the visual interface, of course, the libraries with info from other projects, and also the project database module. And all the results that show are all in diagrams, especially the key system results, the energy supplied, and storage temperature. And we move to the energy service companies that provides different services. One is the most used, the energy management. The other one is the maintenance, the full warranty repair, and the improvement works and renewal. You can choose all these elements or only one, and they provide mainly this heating and electricity sources. And then the last that I haven't finished 100% because it was too quickly, that we had different projects from that was explained by Alejandro Del Amo, Agora Solar. They have different ones. We have the British School in Aragon and ARPA and the University of Zaragoza and another hospital. I have to finish the drawing here. In all of them, they use the heat storage in the summer, and also he also commented that in general, in all tender proposal, they try to be more into, award this kind of projects when it comes to renovation or new buildings. And that's all. I hope I didn't, another questions and answer will become afterward. Well, thank you so much. I hope I went through all the key elements, and this will be sent together with the summary. And I don't know, Ariane, it's not your voice to explain how we're going to move forward on this, to move on this on the conference. Thank you so much.
Thank you very much, Alejandro. Wow, I love it. It's very nice, very good summary, and very beautiful. So it will help us communicating the project. Well, we are going to publish it in our website and social media accounts. So thank you very much. And now, well, we are in the end of the conference. Thank you very much to all the speakers and all the people who have been here today with us. Thank you special to the two Alejandros, one from Alberto Solar and from Ale Drawings. We are going to send you the presentations and the other material used today. And we will mail you the official email to contact us, and we are going to collect the questions and give you feedback, of course. And well, long life to Chess Setup, and we have prepared a video for summarizing the project as well. We are going to pass it now, and you are welcome to stay and watch it. If not, thank you very much for being here today. And well, knowing that the video and the brochures are going to be in the website as well and the social media. Thank you very much. I'm going to share now the video, and have a very good night.
The building sector represents 40% of the energy consumption in the European Union. The building sector represents 40% of the energy consumption in the European Union and is also responsible for 36% of the total CO2 emissions. That is a lot, isn't it? SETUP is a Horizon 2020 project that has designed a solution that increases the efficiency, the self-sufficiency and the renewables implementation in buildings. To make this possible, a group of 10 partners from 5 different countries have come together, from public entities as municipalities or agencies to universities or private enterprises. But how does it work? We need solar panels and a thermal storage with a heat pump in a building connected to the grid. The solar panels transform the radiation from the sun into heat to be used for domestic hot water and heating. The seasonal storage tank then collects the heat and increases the temperature of the medium. With the help of a heat pump, the heat is transferred to the building with a very low consumption. When needed, the energy is used in the building, and if there are surpluses, the energy can be stored in batteries or injected to the grid. Chess Setup has been tested in 3 pilot sites.
The challenge is to achieve of energy demand of the center. This is expected to produce 80% of the total energy demand for cover 100% of summertime. The 3 main elements of the system are the heat pump, which will be considered a line of the system, energy storage tank, 100 cubic meters, and the production of green energy by heating the panels. This allows not only to produce the expected thermal energy, but also electrical energy necessary for the operation of the system with a surplus that can be counted to the total installation.
located in Manlleu, Spain. It consists of a photovoltaic array of 9.9 kilowatts, which feeds an efficient air source heat pump to heat the thermal storage. Construction works finished in August 2019, and since then, energy savings of 26% have been achieved. In conclusion, CHESS setup can allow significant energy and emissions savings for buildings. The pilots have shown that it is a suitable technical and environmental solution, as well as economically viable. CHESS setup brings key solutions for our future, a system that could help driving us towards nearly energy zero buildings and a low carbon society for all.
Well, thank you very much. That was the video. I think that maybe for the Zoom connection, the voice was not great, but it's going to be published in the website and communicated by our social media channels. And I repeat again that we are going to send an email to you with all the presentations, questions resolved, and any question you might have, you can contact us. Thank you very much for being here today, sorry, and have a great weekend, everyone. Thank you very much.
Thank you, Ariana, for the job.
Thank you, Ariana.
Thank you. Bye-bye.
Thank you, everyone.
Thank you. Bye.
Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.